Welcome back again, everyone. You're now tuning in to Sip&Talk. This is Sunny.
And I'm Joe, 434 episodes in.
Great.
Okay, so the tech world has been buzzing lately, hasn't it? It feels like something big just happened.
Oh, yeah. Everyone's throwing around AI revolution, but honestly, the latest stuff from NVDA, that feels like the actual big bang. For real this time.
I totally get that feeling. It's not just, another upgrade. This feels different.
Exactly. We're talking about their announcement for, what they're calling the Earth's strongest supercomputer.
The Ruben system, right?
That's the one. And the headline number is just wild. It's supposed to be 100 times faster than the DGX-1 system they launched, 10 years ago?
100 times in a decade. That's hard to even wrap your head around.
It really is. And the key thing to understand is why this is happening now, why this massive leap.
It's because the old way stopped working, basically. Moore's law.
Pretty much. Moore's law, the idea that you just keep shrinking transistors to make chips faster and denser, it's hit some serious physical walls. You just can't keep making things smaller indefinitely.
The magic ran out.
Yeah, the magic ran out on that particular trick, yeah. So the game isn't about tiny increments anymore. It's a whole new playbook. Which is
accelerated computing. That's the term they keep using. And AI self-learning stuff.
That's it. Exactly. Yeah. We're shifting away from those general-purpose chips, the ones that do everything okay but one step at a time.
The jack-of-all-trades chip.
Right. And moving towards these highly specialized processors, usually GPUs, designed to handle tons and tons of data all at the same time, in parallel. That's what lets them essentially think and learn in a way the old chips just couldn't.
So it's not just about doing calculations faster. It's like building the intelligence right into the machine's structure.
You've got it. It's a deeper change. And that's really why we wanted to, spend this session digging into it.
Right. So our plan today is to unpack this whole compute revolution. We'll start with the tech itself, what makes it tick.
Yeah, the nuts and bolts.
And then zoom out to see why these changes are shaking up everything, the economy, jobs, even global power dynamics.
It really is a new game. It's about who has the smartest, fastest infrastructure. It's a big deal. Let's break it all down for you.
Okay, let's start with that term. Accelerated computing. You said it's different from Moore's law. For someone who isn't, designing chips for a living, what's a good way to picture that difference?
Okay. Maybe think about it like labor specialization. Imagine the old way. General computing is like having one super smart, very capable worker.
Okay.
But this worker has to do everything. Filing, answering phones, complex math problems, making the coffee, you name it. They do it all.
Right.
But one task after another. Versatile, sure, but slow overall because they're always serving contexts.
Right. A bottleneck. Even if you hire 10 of them, there's still individuals working through their own lists.
Exactly. Now, accelerated computing, which is really driven by GPUs, graphics processing units, and this software layer called CUDA.
CEA, that's NVIDIA's thing, right? The software that makes the hardware work for AI.
That's the crucial link. CUDA lets developers program these specialized chips. So accelerated computing with GPUs and CUDA. That's like having thousands of workers, but each one is highly specialized. One only does filing really fast, another only does calculations, another just handles, data sorting. And critically, they all work at the same time, in parallel.
So the total amount of work getting done just skyrockets.
Exponentially, yeah. The throughput is massive compared to the single worker model.
So GPUs are the specialized hardware workers, and CUD is like the super efficient operating system, or maybe the foreman telling them all what to do and coordinating everything.
That's a great way to put it. Foreman or OS, yeah. And this whole architectural shift, moving to parallel processing, that's what enables the big software change, too.
Which is?
Instead of programmers writing out super detailed line-by-line instructions for every little thing.
Traditional coding.
Right. Now, you can often just feed massive amounts of data to these AI agents, these models running on the GPUs, and let them learn how to do the task themselves.
Less direct instruction, more learning from examples?
Exactly. It's a shift from explicit programming to learned intelligence.
Okay, so that massive speed up, that parallel processing power, that's why we need something like the Ruben system. You called it a technological supercar earlier. Beyond just being 100 times faster, what makes its design special for this kind of work?
Well, a few things stand out. It's all built for running these incredibly power-hungry chips reliably and at massive scale, like 100% liquid cooling.
Liquid cooling, like in a high-end gaming PC.
Sort of, but on an industrial scale. Think about data centers packed with thousands of these chips running full tilt. They get incredibly hot. Air cooling just becomes really inefficient, noisy, and frankly, prone to problems.
Right.
Liquid cooling is much better at pulling heat away directly, keeping the chips running stably within their optimal performance range. It's like cooling a Formula One engine versus a regular car engine.
Okay, makes sense for performance.
Yeah.
What else?
They also mentioned the design of the actual server trays, the bits you slide into the racks. They're designed to be basically wire-free and easy to install.
Why is that a big deal?
Scale. When you're installing not 10, but 10,000 of these units in a massive data center, simplicity matters. Fewer cables means fewer things to connect wrong, fewer points of failure, faster deployment, easier maintenance. It reduces complexity enormously.
Right, building these things isn't like setting up a home network, it's industrial.
Totally. And then inside these systems, the real magic or the real specialization comes from the new types of processors they've introduced. It's way beyond just having a fast CPU and a fast GPU.
Okay, specialized brains, what are they?
This is where it gets really interesting for AI performance. They've unveiled two key new types of specialized processors. First, there's the context processor.
Context processor, what does that do?
Think about how you interact with a good AI assistant now. To give you a smart, relevant answer, it often needs to understand a lot of background information, right?
Yeah, like my previous emails or the company's whole knowledge base or maybe a long document I just gave it.
Exactly. Massive amounts of context. This context processor is specifically designed to ingest, filter, and kind of pre-process all that background stuff, documents, videos, data logs, really, really quickly.
So it pre-digests the background reading.
That's a perfect analogy. It's like a super fast research assistant that reads and summarizes the entire library before the main AI philosopher starts thinking about your specific question. It means the main AI brain gets the relevant info instantly.
That sounds incredibly useful. Okay, what's the other specialized processor? You said it was maybe even more critical?
Yeah, this one's called the BlueField-4 processor, and this is aimed at solving a really tricky bottleneck in AI today, something called the KV caching problem.
KV caching problem. Okay, that sounds technical. We might need to slow down here.
Yeah, let's break it down. It's actually fundamental to how current large AI models work, especially language models.
Okay, lay it out for us. Why does AI memory get slow?
Imagine you're having a long conversation with an AI, or it's processing a really long document. For every new word or piece of information it processes, it needs to refer back to the information that came before it. That's its memory or context.
Right, it needs to remember what was said earlier to make sense.
Exactly. Technically, this recalled information is often stored as key value pairs, or KV pairs. Now, here's the problem. The computational cost of storing and, more importantly, retrieving these KV pairs grows really, really fast as the conversation or document gets longer. The context window size increases.
So the more the AI needs to remember, the slower it gets at remembering.
Precisely. The process of managing this KV cache, this short-term memory, becomes incredibly inefficient. It starts eating up more and more of the main GPU's time and memory bandwidth, eventually becoming the main bottleneck. The GPU itself might be super fast, but it's spending all its time waiting for memory lookups.
Okay, so the chip speed doesn't matter if fetching the relevant memories is like sipping information through a tiny straw.
That's a great way to put it. The Ferrari engine being fueled by an eyedropper, it stalls the whole process.
So BlueField-4 fixes the eyedropper problem.
That's the idea. BlueField-4 is a dedicated chip, a separate brain, designed specifically to handle this KV, caching the storing, managing, and retrieving of that conversational memory. It radically speeds up how the AI accesses its recent history.
And it takes that burden off the main GPU.
Exactly. It offloads that huge memory management headache from the GPU, freeing the main processor up to do what it does best. The actual computation, the reasoning, the generation of new information. It's a hardware solution to a major AI scaling problem.
Wow. Okay, that feels like a really fundamental improvement, especially for making AI conversations smoother and handling much larger amounts of information.
It's potentially a huge unlock, yeah.
But even with these super specialized brains, the main GPU, the context processor, the BlueField-4, they all need to talk to each other instantly, right?
Oh, absolutely. The interconnects, the networking between the chips and between the servers are just as critical as the processors themselves. These specialized brains are useless if they're shouting into a laggy void.
So what are they using for that? Just faster Ethernet?
No, it's way beyond standard networking. They have their own high-speed interconnect technologies, things like ConnectX, Spectrum X, and the quantum switch.
Quantum switch. That sounds futuristic.
Well, the names are fancy, but the function is critical. Think of these not as just cables, but as purpose-built superhighways designed for incredibly low latency. We're talking sub-nanosecond delays and massive bandwidth between potentially tens of thousands of chips working together in a giant system.
So if the communication stutters even for a fraction of a second,
the whole parallel calculation falls apart. The synchronization is lost, and the supercomputer effectively grinds to a halt, or at least becomes wildly inefficient. These switches are the high-speed traffic control system preventing computational gridlock on a massive scale.
Okay, that makes sense. It's the whole system, not just one part. And speaking of future tech and infrastructure, they're not stopping at just refining current AI. They're already building bridges to the next big thing, quantum computing.
Yeah, this is another really forward-looking piece. What's interesting is how they're approaching quantum right now. Everyone knows quantum processing units, QPUs, have the potential to solve certain problems incredibly fast. Problems that are impossible for classical computers.
Right.
But they're also notoriously tricky. Very error-prone, very sensitive, need super cold, controlled environments. They're not quite ready for reliable, independent work.
So the QPU is like this super talented but kind of erratic kid genius.
That's the analogy we were kicking around, yeah. And in NVIDIA's hybrid approach, the powerful GPU supercomputer acts as the coach for this kid.
The coach? How does that work?
Yeah. The GPU system plays a vital role. It handles error correction, constantly checking the QPU's fragile calculations. It manages AI calibration to fine-tune the quantum process. And it provides overall control, managing the workflow, feeding the QPU problems it's good at, and integrating the results. It basically provides the stable environment and guidance the QPU needs to function effectively.
So it's not QPU or GPU, it's QPU plus GPU working together.
Exactly. A hybrid architecture designed for pragmatism, leveraging quantum's potential while mitigating its current weaknesses using mature, powerful classical computing.
And they even developed a specific connector for this, the MVQ link.
Right. That's their specialized interconnect designed specifically to create a seamless, high-bandwidth link between these unstable QPUs and their GPU coaches. They're talking about it potentially supporting systems with, tens or even hundreds of thousands of quantum bits or qubits down the line.
Which raises the question, why pour resources into this now? If commercial quantum computing is still, 5-10 years away, maybe?
It's a strategic infrastructure play. Look at the market projections for the kind of extreme parallel computing needed just for AI data centers. People are talking trillion-dollar markets within the next decade.
Okay.
Building this hybrid QPU-GPU platform now, even before quantum is fully mature, positions them to own the foundational architecture for that future market. They're building the on-ramp for whenever quantum truly takes off commercially. It's a long bet, but potentially a massive one.
It really drives home that NVIDIA sees themselves as more than just a chip company. They're building the entire ecosystem, the whole stack.
Absolutely. It's hardware plus software plus the whole developer ecosystem around it. They're not just selling silicon, they're selling a platform.
How do they make sure developers stay locked into their platform, though? Especially when competitors are also making powerful chips.
The key is CUDA. We mentioned it earlier. That proprietary software layer, the API that developers use to program the GPUs for AI and scientific computing, that's their strategic moat.
Because everyone already knows how to use it.
Exactly. There's this massive global community of developers, researchers, data scientists who are fluent in CUDA. So when NVIDIA introduces a new hardware innovation, like the BlueField 4 for KV caching or the context processor,
it slots right into the existing CUDA framework.
Precisely. Developers can immediately take advantage of it without having to learn a whole new programming paradigm. That integration makes switching platforms incredibly difficult and costly for developers and companies. It creates powerful platform lock-in.
But part of building that community love, presumably, is their work in open source. They seem to be quite active there.
They really are, and it's a smart strategic move. They know they can't invent everything themselves. The stats they share are pretty impressive, talking about over 1,000 open source tools on GitHub, contributing to over 500 models and 100 datasets on Hugging Face, which is a major hub for AI models.
And they're adding a lot regularly.
Yeah, apparently they rank second globally in the number of daily code additions or repository additions on Hugging Face over the last year. They are actively putting a lot of code and models out there for free.
Why do that? Why give away valuable models and tools? Doesn't that help competitors?
It does, indirectly, but the strategic value for them is huge. Open source models are crucial for smaller players and niche industries. Think about, say, a startup doing specialized medical image analysis, or a university lab working on climate modeling.
They can't afford to build giant foundational models from scratch.
Right, but they can take a powerful open-source foundational model that NVIDIA might have contributed to, and then fine-tune it with their own specific domain expert data. This lets them create really strong specialized AI tools much faster.
And because those tools likely run best on NVIDIA hardware using CUA.
It reinforces the ecosystem. It builds goodwill, accelerates innovation across the board, and ultimately keeps more people using and relying on their platform. It's enlightened self-interest.
This platform strategy extends right into building actual supercomputers for national projects too, doesn't it?
Oh, absolutely. They're working directly with places like Los Alamos National Laboratory, partnering with companies like HPE to build the next generation of national supercomputers. Systems like Mission and Vision based on this new Vera Rubin platform.
And these aren't just general-purpose machines.
No, they're specifically designed for intense workloads. They mention direct liquid cooling being key for AI-driven scientific discovery and, importantly, for national security applications.
The scale is just immense. I saw a mention of the Solstice system for the Department of Energy planning to install something like 100,000 Blackwell GPUs.
Yeah, the numbers are staggering. 100,000 GPUs working in concert.
What kind of problem even needs that much parallel power?
You're talking about the grand challenges of science and engineering, simulating climate change with unprecedented accuracy, managing nuclear stockpile safety through simulation instead of testing, discovering new drugs and materials by modeling molecular interactions at massive scale.
Stuff that's just impossible otherwise.
Exactly. Or training the absolute largest, most complex next-generation foundation models, perhaps for intelligence analysis or defense strategy. That kind of sheer computational force is needed for those frontier problems.
Okay, shifting from the purely digital world of simulation to the physical world. Robots.
Yeah.
Their push into physical AI seems to involve a more complex setup. They talk about a 3-computer architecture.
Yeah, this is really interesting. For robots that operate in the real world, think factory automation, warehouse logistics, maybe even surgery bots someday. They argue you need 3 distinct types of computing working together.
Okay, what are the 3 parts?
First, you need the heavy-duty training compute. That's where chips like Grace Blackwell come in. These are the massive systems used in data centers to train the foundational AI models, teaching the robot the basics of perception, physics, and movement planning. That's step 1. The initial learning.
Okay, train the brain. What's next?
Step 2 is simulation and refinement. This is where Omniverse comes in.
Omniverse. That sounds like a metaverse thing. What is it really?
It's essentially NVIDIA's platform for building and running digital twins. Think of it as an incredibly sophisticated simulation environment. It combines generative AI, realistic physics simulation, graphics rendering, sensor simulation, everything needed to create a perfect virtual copy of a real-world environment.
Like a virtual factory floor. Or a virtual operating room.
Exactly. And why is this simulation, this digital twin, so critical for physical AI?
Let me guess. You don't want your expensive robot learning by crashing into things in the real factory. Or worse, making mistakes during virtual surgery practice.
Precisely. Safety and cost. You can train and test the robot's AI models thousands, even millions of times in this virtual world under every imaginable scenario with realistic physics making sure it's safe, efficient, and precise before it ever touches a real object or patient.
So you iterate and fix bugs in the simulation, which is way faster and cheaper.
Dramatically faster and cheaper. It's essential for developing reliable physical AI.
Okay.
The third piece is the computer that actually goes on the robot itself. That's the Thor Jetson platform.
Thor Jetson.
Yeah. This is designed to be a relatively low-power, rugged, real-time computer. It takes the intelligence trained on Grace Blackwell and perfected in Omniverse, and it runs it efficiently right there on the edge device, the robot moving around the warehouse, the drone inspecting equipment, the autonomous vehicle. It executes the learned behaviors in the physical world.
That whole pipeline, the potential market, seems enormous, especially when you hear buzz about humanoid robots.
It really is. Forecasters are talking about humanoid robots becoming potentially one of the biggest new markets, both in consumer electronics, imagine robots helping around the house, and in industrial equipment, taking over repetitive or dangerous tasks.
And NVIDIA is positioning itself to be the brain inside those robots.
That's the goal. Their collaborations with companies like Figure AI, which is working on humanoids, and even Disney Research, exploring robotics for entertainment. It shows they're serious about being the compute platform for physical automation.
They're also making a big play in standardizing autonomous driving, the whole robo-taxi idea, with their Drive Hyperion platform.
Yeah, standardization is absolutely key there, especially given the safety requirements. Hyperion isn't just the computer, it's a whole reference platform. It includes a standardized kit of sensors, cameras, radar, LiDAR, plus the compute hardware needed to process all that data safely and reliably.
So car manufacturers don't have to reinvent the wheel or the sensor suite.
Exactly. Major players like Lucid, Mercedes-Benz, Stellantis, they can adopt the Hyperion platform and focus their engineering efforts on developing their unique driving algorithms and software, rather than spending billions designing and validating the underlying hardware and perception stack. It accelerates development.
And the scale they're aiming for is clear from partnerships like the one with Uber.
Oh, the Uber deal is a massive signal. They're not just providing the platform, they're working to integrate these Drive Hyperion-powered vehicles into Uber's network. And Uber's stated plan is to deploy something like 100,000 robo-taxis using this tech, aiming to start around 2027.
100,000 robo-taxis. That's moving way beyond just pilot programs. That's aiming for real commercial scale. Fast.
It signals huge confidence in the technology's readiness for prime time, or at least imminent readiness.
Okay, let's shift gears and talk about the money. Because when you talk about 100,000 GPUs for one project, 100,000 robotaxis, we're talking about absolutely massive amounts of capital reshaping the economy.
The numbers are just staggering. Look at the projections just for NVIDIA's new Blackwell and Ruben series chips. They're forecasting potential business orders reaching something like $500 billion by the end of their fiscal year 2026.
$500 billion for just those product lines.
Yep. And they point out that's roughly 5 times the growth rate they saw with their previous generation, the Hopper series. That insane acceleration in demand is why you're seeing NVIDIA's valuation explode the way it has.
Which naturally brings up the big question everyone asks. Is this just another tech bubble? Is it like the dot-com craze in 1999, all hype and speculation destined to crash?
It's the elephant in the room, for sure. Jensen Huang, NVIDIA's CEO, has been arguing pretty strongly against the bubble comparison.
What's his argument?
He frames it not as hype, but as a necessary fundamental transition. His point is that the old way of computing, driven by Moore's law, has genuinely hit its limits. And for the global economy to keep growing, for industries to keep innovating, they have to switch to this new model of accelerated computing.
So it's not optional, it's mandatory infrastructure spending.
That's the argument. He says the reason companies are willing to pay such high prices for this technology isn't speculation. It's because the tech actually works and delivers tangible value today.
But hang on, didn't people say similar things in the late 90s? Weren't people paying crazy prices for internet companies with, let's be honest, pretty unproven business models back then? How is this different?
That's a really fair point. The distinction Huang and others draw this time lies in how AI changes the actual labor equation.
How's that?
Back in 1999, the internet was primarily a tool. A powerful tool, yes, it connected people, information flowed faster, but it was still mostly humans using the tool. The argument today is that AI, especially generative AI running on these accelerated systems, isn't just a tool, it's starting to act like a worker. It can perform reasoning, generate complex creative outputs, manage entire workflows, make scientific discoveries.
So it's replacing or augmenting labor costs directly.
That's the core economic argument. Take drug discovery, for example. Investing, say, $10 million in AI compute infrastructure might allow a pharma company to identify promising drug candidates in months, a process that might have taken years and cost hundreds of millions in manual lab work and human researcher time before.
So the return on investment is direct, measurable, and happens quickly.
Exactly. It's enabling breakthroughs and efficiencies that were literally impossible before. So the argument goes, companies aren't just happily paying for these AI systems. They need to pay for them to stay competitive because the productivity gains and cost savings compared to traditional labor are so immense, it's shifting capital allocation away from people and towards compute power.
Okay, I can see the argument for why it might be different this time, based on that worker capability. But even if NVIDIA is reaping huge rewards, this whole build-out must be lifting other boats too, right? It's a whole supply chain.
Oh, absolutely. This is a massive systemic investment. It's not just chips. Think about the physical infrastructure needed. Reports suggest that global spending on just the construction of AI-related infrastructure, new data centers, advanced cooling systems, network upgrades, even securing the energy supply, has already hit around $75 billion.
$75 billion just on the buildings and pipes and wires.
Right. It's a foundational boom. So beyond NVIDIA, who else is benefiting massively from this whole accelerated ecosystem?
Yeah. Who are the key players in this gold rush, besides the ones selling the pickaxes?
You can kind of break it down. First, in semiconductors and manufacturing, TSMC is absolutely critical. They're the main foundry actually manufacturing these incredibly complex Blackwell chips for NVIDIA. You also have memory makers like Micron benefiting hugely from the demand for the high bandwidth memory these systems devour.
Okay, chip makers and memory. What about the connections?
Right, those superhighways we talked about.
Yeah.
In high-speed interconnects, companies like Broadcom and Marvell are key suppliers of the specialized chips and optics needed for that lightning-fast communication between GPUs and servers.
Got it. And the big cloud companies?
Definitely. The cloud providers, Microsoft Azure, Amazon AWS, Google Cloud, they are spending billions buying these NVIDIA systems and integrating them into their own platforms to offer AI services to their customers. They're arguably NVIDIA's biggest customers right now.
And finally, the company's actually putting the pieces together.
Yep, the AI server manufacturers. Companies like Supermicro and HPE, who are also partnering with NVIDIA on those national supercomputers, they're the ones physically building, assembling, and testing these complex server racks filled with GPUs, cooling, networking. They're seeing enormous demand, too.
Wow. It really is a whole ecosystem firing on all cylinders. But what about the actual investors, the traders managing billions? How are they feeling about this? Are they just blindly piling in, or is there some nervousness under the surface?
The sentiment seems to be bullish, but definitely nervous, very cautious. You see surveys where maybe 2/3, like 67% of traders admit they think the sector, especially some of the big names, might be overvalued.
So why are they still in?
Because, for now, tech, led by NVIDIA and a few other giants, is what's driving the entire S&P 500 rally. You feel like you have to be involved, but they're not just buying and holding passively.
So how are they playing it?
Many are using complex options strategies, either to hedge their bets, protecting downside if there's a correction, or even using options as a replacement for owning the stock directly, trying to capture upside with less capital at risk.
So, like the saying goes, dancing while the music's playing, but keeping one eye on the exit.
That's exactly the mood. Enjoying the party, but very aware it could end abruptly. Keep your coat and keys handy.
And this caution isn't just in the stock market, right? What are the bond markets, the fixed income folks, saying? They usually sniff out trouble first.
They're definitely sounding some alarm bells, or at least raising some serious questions. A key concern for fixed income analysts is the sheer amount of debt being taken on to finance this massive AI infrastructure build-out.
More debt than usual.
Apparently, the total debt load specifically tied to this AI boom now exceeds the total debt held by the entire traditional financial sector, banks, insurance companies, etc.
Wow. That's a lot of borrowing.
It is, and it forces a critical question. Is this the very beginning of a long, sustained, decade-plus boom where this debt is easily managed? Or are we adding all this leverage later in the economic cycle when risks are higher?
And the language they use suggests they're worried.
Very much so. You hear analysts saying that credit spreads, basically, the extra interest companies have to pay to borrow compared to the government, which reflects perceived risk, are currently priced to perfection.
Priced to perfection.
Meaning the bond market is assuming almost zero chance of things going wrong. No recession, no defaults, no unexpected inflation spikes. It assumes smooth sailing ahead.
Which sounds optimistic.
Extremely optimistic. It means the market is very vulnerable. If anything significant goes wrong, a global slowdown, maybe unexpected inflation forces rates higher, again, those credit spreads could blow out very quickly, making all that debt suddenly much, much more expensive to service or refinance. It's a point of fragility.
Okay, when you're talking about trillions in investment, massive debt loads, and foundational technology, this stops being just a business story and becomes geopolitical, doesn't it? National strategy.
Absolutely. It's crystal clear that governments now view this kind of computing power as a core strategic asset, like oil reserves or military strength. And you see NVIDIA making moves that reflect this, their push into 6G telecom technology, for example.
How is 6G related to national strategy?
It's about reclaiming technological leadership and reducing reliance on foreign infrastructure, particularly from competitors like Huawei in China. NVIDIA launched this initiative called ARC, which stands for Aerial Radio Network Computer.
ARC, okay.
It's basically a software-defined, programmable computer platform designed specifically for building next-generation 6G wireless networks, heavily integrated with AI. The explicit goal is to help restore U.S. and allied leadership in the global telecom infrastructure space.
And their investment in Nokia seems to fit right into that strategy.
Exactly. They made a significant, reportedly $1 billion equity investment in Nokia. Nokia is, the third largest telecom equipment maker globally?
Right.
This partnership is highly strategic. It aims to create a strong, viable, non-Chinese option for countries around the world, especially in Europe, the Middle East, Africa, when they're building out their 5G and future 6G networks. It's about securing critical infrastructure supply chains.
How does AI actually make 6G better or more efficient than, say, 5G?
It's about optimization. The ARC platform uses AI techniques, particularly something called reinforcement learning, to dynamically manage really complex aspects of radio transmission in real time, like beamforming, which is precisely focusing radio signals where they're needed instead of blasting them out everywhere.
And that saves power or increases speed.
Both, actually. Wireless networks are incredibly power hungry. They consume something like 1.5% to 2% of all global electricity right now. By using AI to optimize beamforming, manage interference, and allocate spectrum much more efficiently, you can drastically reduce energy consumption and increase the network's overall capacity and speed. It's a huge win for cost and sustainability.
And this advanced 6G network then becomes the backbone for other advanced tech.
Precisely. Think about all those physical AI robots and digital twins we talked about. They need ultra-low latency, high-bandwidth connections to function in real time. By pushing compute power out to the edge, integrating it into these 6G base stations, the ARC platform helps create what they call edge industrial robotics clouds.
So the factory robot's brain can partly live in the local cell tower, essentially.
Kinda, yeah. It allows for much faster response times than going all the way back to a distant cloud data center. It's essential plumbing for the next wave of automation.
Beyond telecoms, they're also embedding this tech deeply into defense and intelligence, right? The Palantir collaboration stood out.
Yeah. That's significant. Palantir builds platforms used heavily by defense and intelligence agencies to make sense of massive, complex data sets. Their ontology platform takes in everything, sensor data, reports, structured data, unstructured text, and helps analysts find connections and generate insight.
And NVIDIA's tech speeds that up
dramatically. By integrating the latest Blackwell GPUs, they're accelerating Palantir's platform to process this deluge of data at, as they put it, light speed. This is aimed squarely at enhancing national security decision-making by getting crucial insights faster.
It really felt symbolic that NVIDIA chose to hold their big GTC conference in Washington, D.C. this year.
Oh, that was absolutely a calculated move, a very clear political statement. It underscores this growing consensus in D.C. that advanced technology like AI and accelerated computing isn't just a commercial sector anymore. It's viewed as a fundamental pillar of national power, geopolitical strategy, and economic wealth. They were speaking directly to policymakers.
Which brings us to the really thorny issue: export controls to China. There seems to be a real tension here, competing viewpoints on restricting access to chips like Blackwell.
It's a huge debate, and there are valid arguments on both sides. It really pits immediate security concerns against potentially longer-term strategic goals.
Okay, what's the argument for tight controls? The national security view.
It's pretty straightforward. You simply cannot allow your most advanced, cutting-edge technology, the chips that provide a clear performance advantage, to fall into the hands of a primary strategic competitor, where it could be used to accelerate their military modernization or potentially be used against you. Therefore, you need strict controls, especially on the highest-end stuff.
Makes sense from a security perspective.
Yeah.
But what's the counter-argument, the Silicon Valley view?
The openness view, or perhaps the market dominance view, argues that being too restrictive could actually backfire in the long run.
How so?
By completely denying access, you create a vacuum. This heavily incentivizes and accelerates China's own domestic efforts to develop alternatives. You basically force companies like Huawei and others to double down on creating their own good enough chips.
And they might eventually succeed.
They likely will, even if they remain a generation or two behind the absolute cutting edge. The argument is that this could lead to a situation where China achieves complete technological self-sufficiency, potentially creating a larger, more independent competitor down the road. This view suggests maybe relaxing controls on slightly older generations, trusting that continuous U.S. innovation will maintain the lead while keeping American tech dominant globally.
It's a gamble either way, really.
It is, and this debate often gets linked directly to domestic policies around talent, too.
How does immigration tie into chip export controls?
Many tech leaders argue strongly that restricting things like H-1B visas for high-skilled workers or making immigration harder in general is fundamentally shooting yourself in the foot when it comes to innovation.
Because innovation relies on global talent.
Exactly. They point to data showing that something like half of all venture-backed tech startups in the U.S. were founded by immigrants. To maintain that technological edge, the argument goes, you need the best brains from around the world, not just those born domestically. Restricting talent flow is seen as counterproductive to staying ahead.
Okay, we've talked about the tech, the money, the geopolitics. Let's bring it down to the impact on people specifically, the labor market. We see these huge efficiency gains from AI, and we also see mass layoffs. How much are those connected?
It's really hard to definitively disentangle standard economic cycle pressures from genuine AI-driven job displacement right now. It's messy.
But the narrative is changing.
Yeah, you see huge companies like Amazon, UPS cutting tens of thousands of jobs. Often the public framing isn't AI took your job. It's more like we're streamlining or we're restructuring for greater efficiency, often with an eye towards leveraging AI in the future.
So AI makes it easier not to rehire after cuts.
That seems to be a big part of it. They might lay off due to slowing demand, but then realize that with new AI tools, they don't need to hire back as many people to handle the workload when demand picks up again. AI raises the productivity baseline.
It's funny, I remember years ago the promise was AI would give us all a 4-day work week.
And yet the reality for many seems to be pressure towards a 100-hour work week, right?
Exactly. Why is that?
It's kind of a productivity paradox. Because AI agents can work 24/7, automating tasks and generating insights continuously, the potential workload for the remaining human managers, strategists, and coordinators often expands rather than contracts. There's always more data to analyze, more AI outputs to review and implement.
So AI hasn't really replaced whole job categories yet, like junior bankers.
Not wholesale, no. The biggest impact so far seems to be augmenting existing workers, making one person capable of doing the work that maybe 2 or 3 people did before, or handling much more complex tasks much faster, fewer people, higher output.
The UPS example you mentioned seems like a really stark case of this efficiency drive leading directly to job cuts.
It was a very clear data point. They explicitly announced cutting, 34,000 jobs, and directly linked it to achieving $3.5 billion in cost savings through increased efficiency, automation, and technological streamlining across their logistics network. It's hard to argue AI and related tech weren't a major factor there.
Okay, shifting from the labor market within countries to the movement of people between countries, we're seeing a global trend of tightening immigration rules. This seems counterintuitive if tech needs global talent.
It does seem paradoxical, but yes, there's a definite trend towards tightening, and Japan's recent policy change is a particularly dramatic example.
What did Japan do?
They significantly toughened the requirements for their business management visa, which is often used by entrepreneurs and investors. The minimum required funding basically jumped 6-fold, from 5 million yen to 30 million yen.
Wow, that's a huge leap, from roughly 35K to over 200K.
Something like that, yeah. And on top of that, they added a new rule. You now must hire at least one full-time Japanese employee to qualify for or maintain the visa.
Why such a drastic change? Japan's famous for needing more workers due to its aging population, right?
It is, which makes it seem strange. But the reasons cited are complex. Part of it seems to be about social pressures, concerns about the strain on local resources, like schools, healthcare, welfare systems, from an increasing foreign population.
Okay, resource strain. What else?
There's also an element of trying to curb perceived policy abuse and improve quality control. By jacking up the financial requirement, they're essentially screening for wealthier, more established entrepreneurs and investors, trying to filter out individuals who might be seen as potentially straining public services or competing for lower-wage jobs.
And unfortunately, there were also mentions of crime being a factor.
Yes, sadly, that was part of the stated rationale, too. Reports mentioned concerns about rising crime rates among some foreign national groups, specifically citing issues like systematic forgery of residency cards and driving licenses by some Chinese nationals, and a relatively high number of Vietnamese nationals involved in illegal work. These incidents, even if involving a minority, can erode public trust and fuel calls for tighter controls.
And this isn't just Japan, right? It's part of a wider pattern.
Not at all isolated. You see similar moves elsewhere. The UK has significantly raised the salary thresholds needed for skilled worker visas. Germany made it harder to get citizenship, requiring longer residency. Canada announced plans to slightly decrease its targets for new permanent residents over the next few years.
So the overall trend is towards making immigration, especially for non-elite workers or those without substantial capital, more difficult.
Generally, yes. The takeaway for you, the listener, especially if you're considering moving abroad, is that immigration policies are very sensitive to economic conditions and social sentiment, and they rarely get easier over time. Historically, the doors tend to tighten. Acting sooner rather than later often involves less risk and fewer barriers.
Sobering thought. Okay, before we wrap up, let's quickly touch on a couple of financial news items that tie into this whole AI power structure story. Microsoft's revised deal with OpenAI seemed important.
Yeah, that was crucial for Microsoft's stability. They essentially locked in their rights to a significant chunk, reportedly 25% of OpenAI's revenue, and, importantly, secured ongoing access to OpenAI's intellectual property, their core AI models, until at least 2032.
Why was that so vital for Microsoft?
Because their entire multi-billion-dollar Copilot strategy across Windows, Office, Bing, etc. relies heavily on OpenAI's technology. This deal ensures they can keep executing that strategy without the risk of OpenAI suddenly changing direction, prioritizing another partner, or cutting off access to the latest models. It secured their critical AI software supply chain.
Makes sense. And finally, what's the latest thinking on the Federal Reserve? Are rate cuts still expected?
The general consensus still leans towards expecting maybe a 25 basis point rate cut at some point, but the Fed's job is incredibly difficult right now.
Why is that?
Well, they've had patchy economic data lately, partly due to things like temporary government shutdowns obscuring the picture. The overall economy has been surprisingly strong, growing near 4%, but parts of the labor market are clearly softening.
So conflicting signals.
Exactly. And the big risk for them is getting overconfident and cutting rates too soon or too much, only to see inflation flare up again later, especially with ongoing risks from tariffs or global supply chain issues. They're walking a tightrope.
Is there also talk about them changing their quantitative tightening policy, QT?
Yes, there's growing speculation that the Fed might soon announce an end, or at least a significant tapering, of quantitative tightening. That's the process where they let bonds mature off their balance sheet, effectively pulling liquidity out of the market.
And stopping QT would put liquidity back in.
Correct. Ending or pausing QT would be seen as a move to ease financial conditions, maybe to prevent any potential funding stresses in the banking system, and perhaps indirectly acknowledging the fragility of those credit markets that are supporting all this massive AI infrastructure investment we've been talking about. It's all connected.
Wow. Okay, that was a journey. From the intricacies of the Bluefield 4 processor solving KV caching, all the way to global immigration policies and Federal Reserve balance sheets.
It really covers a lot of ground, doesn't it? But the central thread is undeniable. This shift towards specialized, parallel, AI-driven computing is not just a tech story. It's the fundamental force reshaping the economic landscape, the job market, and even the balance of global power for probably the next couple of decades. We're past the point of no return.
Definitely feels that way. And just to reiterate for everyone listening, our aim here on Sip and Talk is always to lay out the facts, the different perspectives, the context as objectively as we can. We're not here to criticize or take sides, just to give you the information you need to think critically about these massive shifts happening around us.
Absolutely. It's about understanding the forces at play. So maybe a final provocative thought for you to chew on after all this.
Okay, let's hear it.
If computing power truly is the new oil, the fundamental resource, and AI is the new engine that runs on that oil, driving productivity and economic value, then how fast does every single industry, from defense manufacturing down to, interior decoration, need to fundamentally overhaul its technological infrastructure before its current way of operating becomes functionally obsolete? Is there a deadline? We're not seeing yet.
Oof. Less like a choice, more like a ticking clock. Definitely something to think about. That's all the time we have for this session of Sip and Talk. Thank you so much for tuning in.
Yeah, thanks everyone. We hope you found this useful.
If you did, please consider subscribing to Sip and Talk wherever you get your podcasts. And also give a shout out to our friend Mickey. Check out his YouTube channel, Mickytolife. He's got great memes, liquor tastings, cool vlogs from around Europe. Always entertaining.
Good stuff over there.
Definitely check it out. We'll be back soon with another deep dive. Until then, take care.
See you next time.